Picture a thread so vast it could stitch the fabric of the universe itself, an invisible ribbon of hydrogen gas, stretching millions of light years between two galaxies, each an island of stars drifting in the cosmic dark. This isn't science fiction, it's real. It's the Intergalactic Bridge, one of the most breathtaking structures in the cosmos, and it's hiding secrets that could rewrite what we know about how galaxies live, interact, and even die. Right now, as you watch this, that bridge is out there, shimmering with the faint glow of primordial gas, a remnant of the universe's earliest days. And today, we're going to cross it together, venturing into the unknown to uncover how something so delicate can bind the universe's largest structures. What makes this bridge so extraordinary isn't just its scale, though that alone is mind-bending. It's the fact that it shouldn't exist at all. By all accounts, the space between galaxies is a howling void, a near-perfect vacuum where matter is so sparse, it defies logic to think anything could span such distances. And yet, here it is, a river of hydrogen flowing against the current of cosmic emptiness, defying the odds. How does it hold itself together? What forces sculpted it? And most tantalizing of all, could it be a clue to something even bigger? A hidden web of connections threading through the entire universe. These aren't just questions for astronomers. They're puzzles that tug at the very human desire to understand our place in the cosmos. This is more than a story about gas and gravity. It's a tale of how the universe builds its grandest structures in the quietest ways, how the tiniest particles can weave the largest tapestries. Over the next few minutes, we'll trace the journey of this bridge from its explosive birth in the chaos of the early universe to its silent role in shaping the galaxies we see today. You'll discover why scientists call it a cosmic lifeline, how it challenges our theories of dark matter, and what it might teach us about the fate of our own Milky Way. So buckle up. We're about to take a voyage across space and time, following a thread of hydrogen that connects not just galaxies, but the past to the present, and maybe, just maybe, the known to the unknown. But this bridge isn't just a lone thread in the darkness, it's part of something far grander. Think of the universe as a spider's web, glistening with dew in the early morning light. Only instead of silk, it's woven from hydrogen gas, and instead of catching insects, it traps entire galaxies in its delicate strands. This is the cosmic web, the hidden architecture of everything. For decades, astronomers assumed galaxies floated like isolated islands in the void. But now we know they're connected by these vast filaments, rivers of gas flowing through the emptiness, linking one galaxy to another in an intricate dance of gravity and time. The intergalactic bridge we've been exploring, it's just one shimmering strand in this colossal tapestry. What's truly astonishing is how these filaments shape the fate of galaxies. Picture a highway system, but instead of cars, it's funneling raw material hydrogen, the fuel for new stars across the universe. Without these cosmic roads, galaxies would starve, cut off from the gas they need to birth new suns. And that bridge between two distant galaxies, it's not just a curiosity, it's a lifeline pumping fresh gas into those galactic ecosystems, keeping them alive. But here's the wild part, we can't even see most of this web directly. The filaments are so faint, they're practically invisible. Scientists had to piece together their existence by studying how galaxies move, how they cluster, how they're pulled by forces we can't see. It's like mapping a city by watching the flow of traffic, not the streets themselves. This discovery turns our old ideas upside down. We used to think of space as mostly empty, with galaxies as lonely points of light. Now we know the universe is buzzing with connections, a dynamic network where everything is linked, and that changes everything. If these filaments guide galaxies, then what we see today, the Milky Way, Andromeda, all the swirling spirals and blazing quasars, might just be the result of where the cosmic web placed them billions of years ago. It's a humbling thought. The very structure of the universe might determine which galaxies thrive and which fade into the dark. And somewhere out there, that delicate bridge of hydrogen is still stretching, still whispering secrets about how the cosmos builds itself, one invisible thread at a time. Hydrogen might seem humble, just a single proton and a lone electron, the simplest atom in existence. But this elemental underdog is the universe's ultimate architect. Picture it as the cosmic equivalent of a single Lego brick, basic, unassuming, yet capable of building everything from newborn stars to the vast bridges between galaxies. In fact, 3/4 of all normal matter in the cosmos is hydrogen, a relic of the universe's fiery birth nearly 14 billion years ago. When the first atoms formed after the Big Bang, hydrogen was the pioneer, the raw ingredient from which everything else would eventually arise. And in the case of our intergalactic bridge, it's not just it's the star of the show, the invisible thread stitching two galaxies together. What makes hydrogen so perfect for this cosmic scaffolding? It's lightweight, abundant, and remarkably stable over astronomical timescales. Unlike heavier elements forged in stellar furnaces, hydrogen has persisted almost unchanged since the dawn of time. And in the emptiness between galaxies, where temperatures hover just above absolute zero and densities are vanishingly low, hydrogen atoms can stretch into wispy filaments, forming structures so delicate they'd vanish if you looked at them too hard. Yet here's the paradox: despite their fragility, these hydrogen bridges wield incredible influence. They're the universe's silent puppeteers, guiding the growth of galaxies by funneling fresh gas into their star-forming factories. Without them, galaxies would exhaust their fuel, their lights flickering out like candles in the wind. But hydrogen's role gets even more fascinating when we consider how it behaves in these intergalactic environments. Unlike the chaotic swirls of gas within galaxies, the hydrogen in these bridges is often eerily calm, stretched so thin that atoms might travel for years without bumping into one another. It's a place where physics operates on a knife's edge, where the gentle tug of gravity battles the expansive pressure of the surrounding void. And somehow, against all odds, the hydrogen holds fast, weaving a bridge that can persist for billions of years. Scientists suspect magnetic fields might play a role, acting like invisible guardrails to keep the gas from dissipating into the darkness. Or perhaps dark matter, that mysterious cosmic glue, helps stabilize these filaments, though no one knows for sure. What's clear is that hydrogen bridges aren't just passive structures. They're dynamic, evolving over time as galaxies move and interact. Imagine two massive galaxies drifting apart, their gravity stretching the hydrogen between them like taffy, thinning it further until it's nearly transparent. Or picture a sudden influx of gas from a nearby cosmic collision, causing the bridge to brighten momentarily as new material surges through it. These aren't static relics, they're living, breathing features of the universe, constantly reshaped by the forces around them. And every time astronomers detect one, it's like finding a hidden chapter in the story of how galaxies grow and change. So the next time you gaze up at the night sky, remember, those distant specks of light aren't really islands. They're connected, bound together by rivers of hydrogen so vast they defy comprehension. And in their delicate strands lies a profound truth, that even the simplest things can build the grandest structures if given enough time and space. The universe wrote its first chapter in hydrogen, and as we're now discovering, it's still writing new ones today. the discovery of these cosmic bridges reads like a detective story, a case cracked not by flashy breakthroughs, but by patient observation and a dash of luck. It began with astronomers peering at distant galaxies through telescopes, not searching for connections between them, but studying the galaxies themselves. Then came the telltale clue, faint fingerprints of hydrogen gas where there should have been nothing but empty space. At first, these wisps were dismissed as artifacts or errors, until they kept appearing over and over, like ghostly threads tying galaxies together. Spectroscopy, the technique that splits light into its component colors, became the key to unlocking the mystery. By analyzing the specific wavelengths absorbed by hydrogen, scientists could map its presence even when it was too tenuous to see directly. What made this revelation so startling was how it upended centuries of cosmic perspective. Since Galileo first turned his telescope skyward, we've imagined galaxies as solitary beacons adrift in darkness. But these faint hydrogen trails painted a different picture, one where galaxies are nodes in a vast network linked by rivers of primordial gas, the real surprise. Many of these bridges were found where no one expected them, stretching between galaxies too far apart for their gravity to easily explain the connection. It was like finding invisible ropes tying together ships miles apart on an ocean, with no clear force holding them taut. The accidental nature of the discovery adds to its wonder. Astronomers weren't even looking for intergalactic bridges when they found them. They were studying quasars' brilliant galactic cores and noticed something odd. The light from these distant beacons showed absorption lines indicating hydrogen gas along the line of sight, but not associated with any visible galaxy. Like detectives tracing a suspect's path, researchers realized this gas wasn't just floating randomly, it was structured, forming coherent pathways between galaxies. The more they looked, the more bridges they found, some stretching over 10 million light-years, remnants of the universe's large-scale architecture. Modern telescopes transformed these faint hints into undeniable proof. Instruments like the Very Large Telescope in Chile and the Hubble Space Telescope acted as cosmic microscopes, revealing details in the hydrogen's distribution and motion. Radio telescopes, sensitive to the faint whisper of hydrogen's characteristic wavelength at 21 centimeters, mapped these filaments in 3 dimensions. Suddenly, what seemed like empty voids between galaxies were bustling highways of gas, flowing at speeds that defied simple explanation. Some bridges showed evidence of turbulence, as if galaxies were tugging on them like children playing with a jump rope. Others were eerily smooth, their hydrogen so undisturbed it might have flowed unchanged for billions of years. This discovery didn't just add a new feature to the cosmic map, it rewrote our understanding of how galaxies evolve. Those faint hydrogen streams are more than curiosities. They're lifelines, channeling the raw material for new stars across unimaginable distances. Galaxies we once thought were isolated are actually participants in a grand exchange, sharing gas through these delicate filaments. And perhaps most remarkably, this hidden web might hold clues to one of astronomy's greatest puzzles: how galaxies get the fuel they need to keep shining across cosmic time. The bridges aren't just connecting galaxies, they're connecting us to a deeper understanding of the universe's hidden machinery. Gravity is the unseen sculptor behind these cosmic bridges, patiently carving them over timescales that dwarf human history. Imagine 2 galaxies drifting apart in the vastness of space, each exerting an invisible pull on the sparse hydrogen between them. Like taffy stretched between 2 hands, the gas distorts, elongating into a filament so thin it would take a starship tens of thousands of years just to traverse its width. Yet this delicate process isn't instant, it unfolds over billions of years. a slow-motion ballet choreographed by gravity's relentless hand. What's astonishing is how gentle this process can be. Unlike the violent collisions that reshape galaxies, bridge formation is a study in cosmic patience. The hydrogen resists at first, its atoms preferring to stay loosely scattered. But gravity persists, gradually herding these wayward particles into coherent streams. Think of it like a river carving a canyon, except here, the water is hydrogen gas, the canyon is light years wide, and the current flows at speeds that would make glaciers seem hasty. Over eons, what began as a faint smudge of gas transforms into a defined highway, its structure refined by the subtle tug of dark matter halos surrounding the galaxies. Here's where things get even more intriguing. These bridges aren't static sculptures, they're dynamic pipelines. As galaxies move, their gravitational dance stretches and warps the filament, sometimes twisting it into shapes resembling cosmic DNA. In denser regions of the universe, where galaxies cluster like fireflies in a jar, multiple bridges can intersect, creating knots of hydrogen that act like interstellar roundabouts, funneling gas in unexpected directions. And just like a rope under tension, these filaments can develop vibrations, subtle waves propagating through the gas, carrying clues about the forces that shaped them. But gravity isn't working alone. Magnetic fields woven through space like invisible spider silk may help stabilize these filaments, preventing them from dissipating into the void. Turbulence from ancient cosmic collisions could ripple through the gas, creating pockets of density that act like gravitational anchors. Even the faint pressure of starlight, photons pushing against hydrogen atoms over astronomical timescales, might play a role in sculpting the bridge's final form. It's a symphony of forces, each contributing its own note to the structure we see today. The true marvel, this process isn't unique. Across the observable universe, countless bridges are being drawn and redrawn by the same forces, a hidden network of gas shaping the evolution of galaxies we'll never see with the naked eye. Every thread we discover rewrites our understanding of how the universe builds its largest structures, not with sudden explosions, but with the patient persistence of gravity, working one atom at a time. Dark matter is the silent architect behind these cosmic bridges, its invisible fingers weaving hydrogen into the universe's grandest tapestries. Picture a sculptor working with clay, except here, the clay is primordial gas, and the sculptor's hands are made of something we can't even see. Dark matter doesn't emit, absorb, or reflect light, yet its gravitational pull is so powerful it bends the very fabric of space, creating gravitational wells where hydrogen gas naturally pools. These wells act like cosmic basins, channeling the flow of gas into the delicate filaments we observe between galaxies. Without dark matter's steadying influence, these bridges would dissipate into the void, their hydrogen atoms scattering like dust in the wind. What's remarkable is how precisely dark matter orchestrates this process. Computer simulations of the universe reveal a stunning pattern wherever dark matter clusters. Hydrogen gas follows, drawn in by gravity's inexorable tug. Over billions of years, these dark matter halos, vast and invisible, become the skeletons upon which the visible universe is built. The bridges we see are just the glowing traces of this hidden framework, like fireflies illuminating the outline of a tree at night. And just as tree branches guide the path of climbing vines, dark matter's gravitational scaffolding directs the flow of hydrogen, ensuring these filaments remain stable across cosmic timescales. Yet dark matter's role isn't just about structure, it's about timing. In the early universe, dark matter acted like a cosmic traffic controller, slowing down the expansion of hydrogen gas in just the right places to allow filaments to form. Without this deceleration, the gas would have raced outward too quickly, leaving no time for gravity to work its magic. It's a delicate balance, one that had to be struck perfectly for these bridges to exist at all. Some scientists even speculate that dark matter's peculiar properties, its reluctance to interact with ordinary matter except through gravity, might be the reason these filaments are so stable. Unlike normal matter, which collides and heats up, dark matter slips through itself effortlessly, maintaining the smooth, sprawling structures we observe. But here's where the mystery deepens. Not all dark matter behaves the same way. Some theories suggest certain types might be warmer, moving faster and making finer, more intricate filaments. Others propose cold, dark matter, sluggish and heavy, which would create thicker, more pronounced bridges. The hydrogen gas threading these cosmic highways could hold the key to telling them apart. By studying how the gas moves, whether it flows smoothly or shows signs of turbulence, astronomers might finally glimpse the true nature of dark matter itself. This interplay between the seen and unseen is what makes these bridges so extraordinary. They're not just celestial curiosities, they're windows into the dark universe, a realm that makes up 85% of all matter yet remains utterly invisible to our telescopes. Every wisp of hydrogen in those filaments is a messenger carrying clues about the forces that shaped it. And as we piece together this cosmic puzzle, one thing becomes clear. The universe is far more connected, far more intricate than we ever imagined. The bridges between galaxies are more than just strands of gas. They are the handwriting of dark matter, a signature written across the sky in atoms older than time itself. Detecting these cosmic bridges is like trying to photograph a whisper in a hurricane. Hydrogen gas between galaxies is so diffuse, it barely makes its presence known. But here's the trick astronomers use. Every hydrogen atom in the universe is a tiny radio transmitter, broadcasting on a specific frequency. When an electron inside a hydrogen atom flips its spin, it releases a faint pulse of radio waves with a wavelength of 21 centimeters, a signature as recognizable to scientists as a fingerprint. Spread across millions of light years, these individual whispers combine into a detectable signal, a ghostly chorus revealing the bridge's hidden contours. Modern radio telescopes act as cosmic eavesdroppers, their enormous dishes tuned to catch this faint emission. Facilities like the Very Large Array in New Mexico or the Meerkat Array in South Africa work like gigantic ears, collecting these whispers over weeks or even months of observation. The data they gather isn't a crisp photograph but a puzzle, a map of radio intensity that supercomputers stitch together into three-dimensional structures. What emerges is astonishing. Filaments that twist like ribbons in the solar wind, regions where the gas bunches up into dense knots and stretches so tenuous they're barely there at all. Some portions of these bridges show turbulence as if something, perhaps a passing galaxy's gravity, has stirred the gas like a spoon in coffee. Other segments are eerily smooth, flowing undisturbed for millions of light years. The real breakthrough came when astronomers realized these bridges aren't uniform pipelines but dynamic, evolving structures. By measuring subtle shifts in the 21-centimeter signal, researchers can track how the gas moves, whether it's flowing toward one galaxy or the other, or caught in a gravitational tug of war. In one startling case, a bridge between two colliding galaxies showed hydrogen racing along the filament at nearly 200 kilometers per second, a cosmic river in flood. Other observations reveal bridges that flicker in and out of detectability, their gas so thinly spread it only becomes visible when backlit by the radio glow of distant quasars, like dust motes caught in a sunbeam. But the most surprising discovery, these bridges are far from pristine. Spectroscopy, the art of splitting light into its constituent colors, unveils trace contaminants in the gas, heavier elements like carbon and oxygen, atoms that shouldn't exist in primordial hydrogen. Their presence tells a dramatic story. At some point, supernova explosions or galactic winds must have blasted these elements into the void, polluting the bridge with the ashes of dead stars. It's a clue that these filaments aren't just relics of the early universe, but active participants in galactic evolution, exchanging not just gas, but the very building blocks of planets and life. The challenge now is pushing our instruments further. Next-generation telescopes like the Square Kilometre Array, with thousands of antennas spanning continents, will detect bridges too faint for current technology, mapping their structure in unprecedented detail. Some astronomers even dream of catching the birth of a new bridge, watching as gravity sculpts raw hydrogen into a cosmic lifeline in real time. Until then, every observation peels back another layer of mystery, revealing how the universe stitches itself together, one invisible thread at a time. If you lined up every intergalactic bridge we've discovered, you'd think you were looking at a gallery of cosmic fingerprints. No two are exactly alike. Some stretch like thick, ropey vines between galaxies, dense enough to birth new stars right there in the void. Others are so delicate they'd vanish if you blinked, mere whispers of hydrogen barely holding their shape against the pull of dark matter. These differences aren't just cosmetic, they're clues written in gas, telling us how the universe tailors its structures to the environment around them. Take the Leo Bridge, for instance, a colossal filament connecting galaxies in the Leo cluster. Packed with enough hydrogen to fuel star formation for eons, it's a cosmic fire hose compared to the wispy tendrils linking galaxies in quieter corners of space. The reason: chaos. In dense clusters like Leo, galaxies jostle like commuters in a crowded train, their gravitational tugs churning the gas between them into dense knots. Turbulence becomes the architect here, compressing hydrogen into thick strands that glow faintly with the birth of new stars. It's a stark contrast to the serene bridges found in cosmic voids, where galaxies are few and far between. There, hydrogen filaments unfold like slow-motion rivers, undisturbed for billions of years, so pristine they still carry the chemical signature of the early universe. But here's what's really fascinating. The weight of a bridge can rewrite a galaxy's destiny. Picture two galaxies connected by a thick, gas-rich filament, a celestial umbilical cord pumping fresh hydrogen into their stellar nurseries. These galaxies become galactic powerhouses, their star formation rates soaring as they feast on the bridge's bounty. Now imagine a different pair linked by a threadbare strand. The gas trickles in so slowly that their star formation sputters, leaving them dimmer, quieter, like embers cooling in the dark. This isn't just speculation. Astronomers have caught this drama in action. In the Virgo cluster, they've watched galaxies on fat, busy bridges churn out stars 10 times faster than their isolated neighbors. Meanwhile, in the sparsely populated Lynx Cancer void, galaxies connected by faint filaments show signs of starvation, their gas reserves dwindling to a whisper. The bridges themselves evolved too, shaped by their surroundings like trees bent by wind. In violent regions where galaxies collide or clusters merge, filaments twist into bizarre shapes, kinked and braided by gravitational shocks. Some even sport beads, dense clumps of hydrogen that glow like streetlights along a cosmic highway. Yet in tranquil voids, bridges remain sleek and straight, their hydrogen so undisturbed it might as well be frozen in time. These differences aren't random, they're testaments to the forces that sculpt them. A bridge's thickness, its turbulence, even its lifespan, all are dictated by the gravitational roughhousing of the galaxies it connects. What's emerging is a cosmic rulebook. The universe builds bridges to match their neighborhoods. In crowded galactic cities, they're robust and chaotic, built to withstand the shoving match of nearby giants. In the boondocks of space, they're fragile and serene, woven with patience over eons. And somewhere in between, there's everything else: bridges that defy expectations, bridges that flicker like candle flames, bridges that might just rewrite the rules we thought we knew. Each one is a laboratory, offering a unique window into how the universe stitches itself together. And as we catalogue their diversity, we're not just mapping gas, we're reading the story of how galaxies grow up, how they're fed, and how they're shaped by the invisible threads tying them to the cosmos. Nothing in the universe lasts forever, not even these cosmic bridges. They may stretch for millions of light years, but time wears them down, unraveling their delicate threads like old ropes left out in the elements. Gravity, the same force that sculpts them, can also tear them apart. Picture two galaxies drifting ever farther from each other, their mutual pull weakening as the expansion of space pushes them apart. The hydrogen bridge between them stretches thinner and thinner, like taffy pulled too far, until it finally snaps, its atoms scattering into the void. Other times, a passing galaxy might sideswipe the filament, its gravity disrupting the gas like a speedboat cutting through a calm river. The bridge twists, knots, or even fractures, its once orderly flow now a chaotic tangle. But the most dramatic end comes when galaxies collide. Imagine two spiral galaxies, each with hundreds of billions of stars, plunging toward each other in a slow-motion cosmic dance. As they merge, their gravitational turmoil churns the hydrogen bridge between them into a storm of shock waves and turbulence. The gas heats up, glowing fiercely before dispersing like smoke in the wind. What was once a pristine filament becomes just another part of the galactic wreckage, its structure obliterated in the violence of creation. Yet even in destruction, there's purpose. That scattered hydrogen doesn't vanish, it becomes fuel for new stars, raw material for the next chapter in these galaxies' lives. The lifespan of these bridges varies wildly, from a few billion years to nearly the age of the universe itself. Isolated filaments in quiet cosmic backwaters can persist almost unchanged, their hydrogen so undisturbed it might as well be frozen in time. Others, caught in the gravitational crossfire of busy galactic clusters, might last only a fraction of that. Astronomers have even spotted bridges in the process of dissolving, their gas frayed at the edges, thinning like morning mist under the sun. These dying filaments are just as revealing as their younger counterparts. By studying how they fade, scientists can piece together the forces shaping the universe's large-scale structure. What's truly remarkable is how much these transient bridges tell us. Like footprints in wet sand, they capture a fleeting moment in the universe's evolution. A thick, star-forming filament might be a snapshot of two galaxies still deeply connected, while a wispy, dissipating strand could signal a relationship on the brink of severance. And sometimes the absence of a bridge is just as telling proof that even the universe's grandest structures are subject to change. These filaments don't just connect galaxies, they connect eras, letting us glimpse how the cosmic web rewires itself over time. So while these bridges may not be permanent, their legacy is. Every wisp of hydrogen, every scattered atom becomes part of something new, a star, a nebula, maybe even the raw material for planets. The universe wastes nothing, and even as one bridge fades, another is forming somewhere else, stitching the cosmos together in an endless cycle of creation and dissolution. It's a reminder that in space, as in life, connections may not last forever, but they always leave their mark. The most astonishing stars in the universe aren't the brilliant ones lighting up galactic spirals or the violent supernova exploding in stellar nurseries, they're the loners. Picture a star glowing softly in the abyss, untethered from any galaxy, born in the frigid emptiness between worlds. These cosmic orphans shouldn't exist. Conventional wisdom says stars form in the dense, bustling neighborhoods of galaxies where gas clouds collapse under their own weight, igniting nuclear fusion. But out there, suspended in the delicate threads of intergalactic bridges, astronomers have found stellar renegade stars that defied the odds by sparking to life in the loneliest places imaginable. How does star formation even occur in such hostile environments? The answer lies in the bridge's hidden complexity. While most of the hydrogen in these filaments is vanishingly thin, gravity occasionally works its magic, coaxing gas into dense knots. Imagine a river with sudden whirlpools, regions where currents conspire to gather floating debris into tight clusters. In these cosmic eddies, hydrogen atoms crowd together just enough to trigger collapse. The process is achingly slow compared to galactic star formation, taking hundreds of times longer, but given billions of years, even the faintest whispers of gas can coalesce into something magnificent. These bridge-born stars are unlike any others. Isolated from the heavy elements forged in galactic furnaces, they're composed almost entirely of pristine hydrogen and helium, relics of the early universe's chemistry. Their light carries the signature of a simpler time before supernova seeded space with carbon, oxygen, and iron. Some might even host planets, worlds formed from the same primordial stuff, though without metals to build rocky cores. They'd be gas giants at best, drifting with their parent stars through the eternal dark. The implications ripple far beyond mere curiosity. If stars can form in the void, then galaxies might not be the sole incubators of stellar life. The universe could be peppered with these solitary lights, a hidden population glowing faintly between the bright islands we've long considered the centers of cosmic activity. Even more intriguing, these bridge stars might serve as stepping stones for future civilizations, offering waypoints for travel between galaxies. Their very existence blurs the line between the emptiness of intergalactic space and the vibrant communities of galaxies. Yet the mystery deepens when we consider how these stars survive. Without the protective cocoon of a galaxy's magnetic fields, they're exposed to the full fury of intergalactic radiation. Cosmic rays and high-energy photons should tear their atmospheres apart, yet some endure for billions of years. Perhaps their sheer isolation shields them, with no nearby supernova or black holes to blast them with extra radiation. They age quietly, burning their fuel at a leisurely pace. Or maybe we're seeing only the lucky ones, the survivors of a much larger population that formed and faded before we ever looked. Every orphan star discovered forces us to rewrite the rules. They're proof that the universe is more inventive than our textbooks, finding ways to kindle light even in the most unexpected places. And as telescopes grow more sensitive, who knows how many more of these cosmic hermits we'll find. Silent witnesses to the fact that star formation isn't just a galactic affair, but a universal one, capable of flourishing anywhere gravity and patience conspire. These cosmic bridges aren't just static marvels, they're galactic recycling plants, shuttling raw material between star systems on a scale that dwarfs human comprehension. Picture a vast conveyor belt stretching through the void, but instead of packages, it's transporting the very ingredients for new stars' hydrogen gas that's been used, ejected, and now reclaimed in an endless celestial cycle. This isn't waste management, it's the universe's most efficient supply chain, operating across millions of light years. When massive stars die in spectacular supernova explosions, they blast their outer layers into space at thousands of kilometers per second. Normally, that gas would drift away, lost forever. But when galaxies are connected by these bridges, the filaments act like cosmic nets, catching this ejected material and channeling it back into circulation. The process works like a slow-motion fountain. A galaxy's active core or supernova eruptions fling gas outward into the bridge, where gravity gradually guides it toward the neighboring galaxy. There, the recycled hydrogen mingles with fresh material, collapsing into dense clouds that ignite as new stars. Astronomers have spotted this phenomenon in action within the Leo triplet, where one galaxy's outflow becomes another's inflow through a shimmering bridge of gas. The mind-bending part: some of those newborn stars may contain atoms that were forged in another galaxy, entirely stellar immigrants carrying the chemical fingerprints of their birthplace across intergalactic space. What makes this exchange so vital is how it sustains galaxies over cosmic time. Left to their own devices, galaxies would eventually exhaust their gas reserves, their star factories grinding to a halt. But these bridges provide a lifeline, topping up their fuel supplies from external sources. The Andromeda Galaxy, for instance, appears to be receiving fresh hydrogen through multiple faint filaments, explaining how it's maintained vigorous star formation long after its peers grew quiet. Even more remarkable, some studies suggest our own Milky Way may be subtly exchanging gas with the Large Magellanic Cloud through an inconspicuous bridge, meaning the next generation of stars in our cosmic neighborhood could contain atoms from a passing satellite galaxy. The recycling isn't always orderly. Sometimes the gas flows in fits and starts, creating bursts of star formation when dense clumps arrive. Other times, the transfer is so smooth it's nearly undetectable, like watching our hand move on a clock. The differences trace back to the bridge's structure. Thick, turbulent filaments deliver gas in dramatic waves, while slender, calm ones provide a steady trickle. There's even evidence that some bridges act as cosmic filters, preferentially channeling certain types of gas while leaving heavier elements behind. This selectivity could explain why some galaxies show unexpected chemical compositions, their stars bearing signatures of atoms that traveled incredible distances before finding a new home. Perhaps the most profound implication is what this says about galactic interdependence. We often think of galaxies as self-contained universes, but these bridges reveal a deeper truth: they're deeply connected, sharing resources across the void like neighbors trading goods over a backyard fence. A star burning brightly in one galaxy might owe its existence to gas expelled from another billions of years earlier. In that sense, the bridges aren't just structures, they're living proof that the universe operates as an intricate web of give and take, where nothing is truly isolated and everything is part of a grand recycling whole. To witness the birth of an intergalactic bridge, you wouldn't need a telescope, you'd need a supercomputer. Across research labs worldwide, scientists are constructing entire virtual universes inside machines, meticulously coding the laws of physics to simulate how these cosmic threads form, stretch, and sometimes snap. These aren't just animations, they're digital laboratories where gravity, gas dynamics, and dark matter interact with precision, allowing astronomers to run experiments that would take billions of years in nature. The results are breathtaking: shimmering filaments of hydrogen emerging from the chaos of the early universe, mirroring the bridges we observe in the real cosmos with uncanny accuracy. The process begins with raw data, measurements of real bridges' density, temperature, and motion fed into equations that govern how matter behaves on the grandest scales. Supercomputers like NASA Pleiades or the European Milky Way then crunch these numbers, dividing the universe into billions of tiny cubes, each representing a parcel of space where physics plays out. Over months of calculation, patterns emerge, gas slowly coalescing into tendrils, dark matter weaving invisible scaffolds, and galaxies tugging at the hydrogen between them like puppeteers pulling strings. What makes these simulations revolutionary isn't just their scale, it's their predictive power. By tweaking variables like the strength of gravity or the amount of dark matter, researchers can test which conditions spawn stable bridges and which cause them to dissolve. One startling revelation from these virtual experiments: bridges are far more sensitive to their surroundings than we thought. In simulations where galaxies cluster tightly, filaments often fray under gravitational strain, their hydrogen shredded by turbulent forces. But in quieter cosmic neighborhoods, bridges grow sleek and stable, some persisting for nearly the universe's entire lifespan. Even more intriguing, certain simulations suggest bridges might self-repair. When a passing galaxy disrupts a filament, surrounding gas sometimes flows in to patch the damage, like cosmic fibroblasts healing a wound. The real magic happens when simulations collide with reality. Astronomers compare these digital bridges to actual observations, checking for mismatches that might hint at flaws in our theories. For instance, when early models predicted filaments thicker than those observed, it forced scientists to reconsider how dark matter interacts with gas. Other simulations revealed hidden bridges too faint for current telescopes' predictions that guided astronomers to eventually spot them. It's a virtuous cycle. Each discovery refines the simulations, and each simulation points to new discoveries. Perhaps the most profound insights come from watching these virtual bridges evolve. Some models show filaments acting as cosmic highways, funneling dwarf galaxies toward larger ones over billions of years. Others capture bridges vibrating like plucked strings after galactic collisions, their oscillations subtly altering the paths of stars. There's even evidence that bridges might seed supermassive black holes, channeling gas into dense knots that collapse into gravitational monsters. Every simulation is a time machine, offering glimpses of futures we'll never live to see, like how the bridge between the Milky Way and Andromeda will stretch and warp as our galaxies hurtle toward collision. What's clear is that these digital universes are more than just tools. They're proving grounds for our understanding of reality. Every pixelated filament that matches a real one validates decades of astrophysical theory. Every deviation sends scientists back to the drawing board, and as supercomputers grow more powerful, these simulations will unlock even deeper mysteries. How the first bridges formed after the Big Bang, how they're entwined with dark energy's expansion, and whether they might one day guide humanity's leap across the intergalactic void. For now, they stand as testament to a profound truth that sometimes, to comprehend the universe's grandest designs, we must first recreate them in silicon and code. Studying these cosmic bridges is like trying to hear a whisper in a thunderstorm. Hydrogen gas between galaxies is so faint, it barely registers against the cosmic background noise. The challenge starts right here on Earth, where our atmosphere acts like a frosted window, distorting and absorbing the very radio waves astronomers rely on to detect these filaments. Even the most advanced telescopes must peer through this turbulent veil, their vision blurred by water vapor and atmospheric interference that can scatter delicate signals into oblivion. It's not just about building bigger dishes, it's about fighting an invisible war against the air itself. Then there's the cosmic cacophony. The universe is a noisy place, filled with pulsars blasting radio bursts, galaxies emitting chaotic static, and even human-made signals from satellites cluttering the data. Isolating the specific 21-centimeter wavelength of hydrogen against this interference is like picking out a single violin in a symphony orchestra playing at full volume. Some observatories retreat to radio-quiet zones, remote deserts or valleys shielded by mountains just to escape Earth's electronic chatter. But space has its own interference. Quasars, supernova remnants, and the afterglow of the Big Bang itself all compete for attention in the same frequency bands. The gas itself is another hurdle. intergalactic hydrogen is so sparse, its atoms might be meters apart, making it 1,000,000 times thinner than the best vacuum we can create in labs. Detecting it requires staring at the same patch of sky for weeks, sometimes months, accumulating photons like drops in a bucket. Even then, the signal is often buried in noise, requiring supercomputers to tease out patterns through statistical wizardry. Some bridges are so tenuous, they're only visible when backlit by distant quasars, their hydrogen casting faint shadows on the brilliant light behind them, like tracing a spider's web by the dew that clings to it. But the greatest challenge might be time. The universe doesn't hurry, and neither can astronomers. Unlike dramatic supernova or colliding galaxies, these bridges change over epochs, not years. Capturing their full story requires patience spanning generations of scientists, with telescopes passing the baton from one observing campaign to the next. A single dataset might take decades to interpret fully, as new algorithms and theories emerge to decode what older instruments recorded. It's a reminder that understanding the cosmos isn't just about technology, it's about perseverance, about stitching together glimpses into a tapestry that no one lifetime could complete. Yet for all these obstacles, the rewards are profound. Every flicker of hydrogen detected, every filament mapped, is a triumph over the universe's reluctance to reveal its secrets. These bridges aren't just scientific targets, they're tests of human ingenuity, pushing us to refine our tools, sharpen our methods, and sometimes to simply wait and listen until the cosmos decides to whisper back. The next generation of telescopes won't just observe these cosmic bridges, they'll dissect them atom by atom, revealing secrets hidden since the dawn of time. At the forefront is the James Webb Space Telescope, with its infrared eyes tuned to pierce through cosmic dust that's obscured our view for decades. Unlike Hubble, which captured these filaments as faint smudges, Webb can map their chemical composition in stunning detail, spotting traces of heavier elements that tell us which galaxies polluted the gas with stellar explosions. Imagine reading a river's history by analyzing individual water molecules. That's the precision Webb brings to these intergalactic highways, uncovering which galaxies contributed material and when. But the real game changer lurks on the ground. The square-kilometer array, a sprawling network of radio antennas across 2 continents, set to become the most sensitive hydrogen detector ever built. Where current telescopes hear these bridges as faint static, the SKA will listen with the clarity of a studio microphone, capturing the subtle Doppler shifts in hydrogen's 21-centimeter signal that reveal how gas swirls and accelerates along the filaments. It's like upgrading from a blurry weather satellite to a high-speed camera tracking every raindrop in a hurricane. The SKA might even catch bridges in the act of forming, spotting the gravitational tremors that first drew hydrogen into coherent streams billions of years ago. These instruments won't work alone. The Vera C. Rubin Observatory, with its panoramic view of the southern sky, will scan for the faint gravitational lensing distortions caused by bridges' hidden mass, indirectly weighing their dark matter content. Meanwhile, NASA's upcoming Nancy Grace Roman Space Telescope will hunt for stars born within the filaments themselves, their ultraviolet glow betraying nurseries where no one thought stars could form. Together, this arsenal of telescopes forms an interstellar forensic team, each instrument contributing a piece to the puzzle, whether it's the gas's temperature, motion, or chemical fingerprint. What's truly exciting are the surprises these tools might uncover. Perhaps bridges contain exotic phases of hydrogen we've never detected, or mysterious magnetic fields that twist the filaments into braids. Some theorists speculate we'll find dark bridges of filaments dominated by invisible matter, where ordinary hydrogen is just a trace contaminant. Others predict telescopes will spot shock waves rippling through the gas, relics of ancient cosmic collisions that sent tremors down these celestial tightropes. The most profound revelations may come from watching bridges evolve in real time. Time domain astronomy, the study of how cosmic objects change, could catch filaments flickering as galaxies tug on them, or gas abruptly surging through them like water through a hose. These dynamic processes, invisible over human timescales, might finally come into view when telescopes compare observations separated by years or decades. It's a reminder that these bridges aren't fossils, they're living structures breathing and shifting as the universe unfolds around them. With each technological leap, we're not just building better cameras, we're constructing time machines. Light from the most distant bridges has traveled for billions of years before reaching our lenses. When future telescopes analyze these ancient photons, they'll effectively peer back to an era when the cosmic web was first being spun, watching gravity's patient handiwork in progress. The data they gather won't just fill textbooks. It could rewrite our understanding of how structure emerges in the universe, why galaxies end up where they do, and whether the threads connecting them might one day guide humanity's journey beyond the Milky Way. The golden age of bridge hunting is just beginning. As these telescopes come online, they'll transform faint hypotheses into concrete knowledge, replacing artists' impressions with razor-sharp reality. What we once inferred from shadows and whispers will soon stand revealed in full-spectrum glory, a cosmic connective tissue more intricate and dynamic than we ever dreamed. And somewhere in that data, hidden among the petabytes of observations, might lie the answer to astronomy's oldest question: how does the universe weave itself together, and what role do these fragile filaments play in its grand design? These cosmic bridges are time capsules, preserving the universe's history in their wispy strands of hydrogen. Every filament tells a story, not just of how galaxies connect today, but of how they've grown, collided, and reshaped themselves over billions of years. Think of them as cosmic growth rings, each layer encoding a different epoch in the life of the universe. When astronomers decode the gas's temperature, motion, and chemical makeup, they're effectively reading chapters from a celestial biography, one that stretches back to when the first galaxies were just beginning to flicker to life. The most astonishing revelation: these bridges act as galactic nurseries in ways we never anticipated. While we've long known that galaxies grow by cannibalizing smaller neighbors or pulling in gas from their surroundings, the bridges reveal a subtler, more elegant process. They're not just passive pipelines, they're active participants in galactic evolution, regulating how and when galaxies receive the raw materials for star formation. Picture a cosmic irrigation system where the bridges act as canals, delivering precise amounts of hydrogen to galaxies at just the right pace. Too much gas too quickly, and a galaxy might erupt in a firestorm of unstable star formation. Too little, and it risks fading into obscurity. The bridges strike a delicate balance, their filaments fine-tuned by gravity to sustain galaxies across cosmic time. This balancing act becomes even more critical when we consider the universe's adolescence, a period known as cosmic noon, roughly 10 billion years ago when star formation peaked. Back then, galaxies were voracious, devouring gas at breakneck speeds, yet somehow they didn't burn out. The bridges likely played a role, acting as safety valves that moderated the flow of gas, preventing galaxies from exhausting their fuel too soon. Evidence comes from quasars, whose brilliant light shines through ancient filaments like headlights through fog. By analyzing how this light is absorbed, astronomers have found bridges from that era were denser and more turbulent, their gas rushing into galaxies like water through a burst dam. Today's calmer, more measured flows suggest the universe has matured, its once ravenous galaxies now fed by a slower, more sustainable trickle. But the story doesn't end there. These filaments also shape the universe's future. As dark energy accelerates the expansion of space, galaxies are being pulled apart, their connections stretching thinner. Some bridges will snap, leaving galaxies isolated. Others might compress as galactic clusters collapse inward, becoming superhighways for gas in the universe's final act. Simulations suggest that in tens of billions of years, the surviving bridges could become the last lifelines for star formation, ferrying hydrogen to galaxies long after the rest of the cosmos has gone dark. What makes this research revolutionary is how it flips our perspective. We used to see galaxies as the protagonists of the cosmic story, with bridges as mere scenery. Now we understand their co-stars, their gravitational choreography guiding galaxies' growth, composition, and even their ultimate fate. Every filament mapped, every gas cloud analyzed, adds another verse to the epic of how the universe builds itself, not in isolated pockets, but through an intricate web of connections that span the ages. And as we unravel their secrets, we're not just studying the cosmos, we're learning how it breathes, grows, and endures. Hollywood might have you picturing these cosmic bridges as glowing highways or shimmering portals, structures so tangible you could theoretically pilot a starship right down the middle. The truth is far more fascinating and in many ways more beautiful. These filaments aren't solid or even dense by earthly standards. Picture the air in the room around you. Now imagine it stretched so thin that each breath would contain just a handful of atoms. That's the reality of an intergalactic bridge. Clouds of hydrogen gas so diffuse, they'd make the vacuum of space inside the International Space Station seem crowded by comparison. If you were to float through one, you wouldn't even know it was there. No resistance, no shimmering walls, just an imperceptible haze stretching for millions of light years. This misconception isn't just harmless sci-fi fantasy. It obscures the real magic of how these structures work. A solid bridge would collapse under its own gravity or be torn apart by cosmic forces. The gas's very diffuseness is what allows it to endure. Each hydrogen atom is essentially free-floating, barely aware of its neighbors, yet collectively bound by gravity's whisper-thin grip. It's like a crowd of strangers spread across an entire continent, all moving in the same direction without ever bumping into one another. That delicate balance between connection and independence is what lets these filaments persist for billions of years, surviving collisions, galactic winds, and the universe's relentless expansion. Another common myth that these bridges are rare. In reality, they're everywhere. We just couldn't see them until recently. The cosmos isn't a collection of isolated galaxies floating in nothingness. It's a bustling network where nearly every major galaxy is linked by these filaments. Our own Milky Way is likely entwined in multiple such connections, though they're too faint for current telescopes to map in detail. What's remarkable is how these bridges challenge our instinct to think in terms of separation. The universe isn't a series of disconnected dots, it's a continuous fabric, with gas threads stitching everything together in an intricate, invisible tapestry. Then there's the persistent idea that these filaments are static, like frozen rivers in space. Nothing could be further from the truth. The gas within them is constantly in motion, flowing, swirling, and sometimes even clumping together into denser knots where new stars ignite. Some bridges pulse with turbulence as galaxies tug on them, while others ripple with shockwaves from ancient cosmic collisions. They're not cosmic infrastructure. They're living, dynamic features, as changeable as weather patterns on Earth, just unfolding over epochs rather than days. The most poetic misconception, though, is that these bridges are mere byproducts of galaxy formation, accidental leftovers from the universe's construction. We now know they're active players in shaping cosmic history. Without them, galaxies would starve, cut off from the fresh hydrogen needed to fuel new generations of stars. They're not just connections, they're lifelines, ensuring the universe keeps evolving, keeps creating. And that's the real wonder, not some sci-fi fantasy of solid arches across the void, but the delicate, invisible threads that quietly bind the cosmos together, atom by atom, light year by light year, in a dance older than time itself. Data becomes art when scientists and illustrators join forces to give form to these invisible bridges, translating cold numbers into visual masterpieces that stir the imagination. Picture this: an astronomer's spreadsheet filled with hydrogen density measurements lands on an artist's desk, and through an alchemy of creativity and precision, those digits morph into a swirling ribbon of gas, glowing faintly against the velvet black of space. These collaborations aren't just about aesthetics, they're a vital bridge of their own, connecting the rigor of astrophysics to the public's sense of wonder. Take NASA Pillars of Creation as a precedent. Raw telescope data, when rendered by skilled artists, became an icon that reshaped how we visualize the cosmos. Now, that same alchemy is being applied to intergalactic filaments, with teams like the Space Telescope Science Institute's Visualization Lab using algorithms to sculpt hydrogen's faint signals into three-dimensional structures we can almost reach out and touch. The process is part detective work, part creative leap. Scientists provide key parameters: gas density, temperature, velocity, while artists confront the challenge of depicting something inherently invisible to human eyes. Some opt for vibrant hues, painting bridges in electric blues and purples to emphasize their dynamism. Others choose subtle gradients, mimicking the faint glow these filaments might emit in reality. The European Space Agency's Cosmic Web project took it further, using virtual reality to let researchers step inside their simulations, surrounded by filaments like threads in a colossal tapestry. These interpretations aren't guesses, they're grounded in data, with every artistic choice vetted against the physics, a slight curve in the filament. That's based on gravitational lensing measurements, a knot of brighter gas. That's where spectroscopy revealed a denser clump. What makes these visualizations so powerful is how they reveal patterns even scientists might miss. When data is plotted on a graph, trends can blend into noise, but when an artist translates those trends into flowing forms, sudden symmetries or unexpected structures leap out. One striking example emerged when a science art team visualized the bridge between the Virgo cluster and a neighboring galaxy group. The filament appeared braided, a twist no simulation had predicted. Re-examining the data, astronomers realized magnetic fields might be shaping the gas in ways their models hadn't accounted for. It was a reminder that sometimes, to see the universe clearly, we need to view it through both the lens of mathematics and the prism of creativity. Beyond laboratories, these artworks ignite public fascination. Exhibitions like The Invisible Universe at Planetarium's worldwide project bridges across domed ceilings, letting audiences fly through them at scales no textbook could convey. Children's books and documentaries now feature these filaments not as abstract concepts, but as tangible, almost familiar structures. The ripple effect is profound. A generation growing up seeing galaxies not as isolated islands, but as nodes in a vast, interconnected web. Even video games and films are taking cues, with sci-fi worlds increasingly depicting realistic cosmic filaments instead of Hollywood's fictional wormholes or warp drives. Yet the most enduring impact might be philosophical. These artistic renderings challenge us to rethink our place in the cosmos. A single image of a hydrogen bridge, stretching farther than our minds can grasp, collapses the distance between human scale and galactic grandeur. It transforms equations into emotion, data into awe, and in that alchemy lies a deeper truth, that the universe's beauty isn't separate from its science but woven through it, waiting for the right collaboration to bring it into view. Science fiction has long toyed with the idea of cosmic bridges, often exaggerating them into glowing superhighways or wormhole-like portals. Think of the mass relays in Mass Effect or the Bifrost from Norse mythology repurposed in Marvel's Thor films. These fictional takes, while far from accurate, reveal something profound: humanity's instinct to visualize connection in a universe that often feels vast and isolating. When Arthur C. Clarke described a bridge of light between worlds in his 1956 novel The City and the Stars, he was riffing on real astronomical theories of his time, the then novel idea that galaxies might be linked by more than empty space. Today's sci-fi authors have richer science to draw from. Alastair Reynolds' Revelation space series features eerie, ancient filaments maintained by alien civilizations, while Lou Sixon's The Three-Body Problem trilogy imagines dark forest theory playing out across these cosmic threads. Video games take the concept even further, transforming bridges into navigable terrain. No Man's Sky lets players fly through colorful intergalactic tendrils, compressing the mind-bending scale into something a ship can traverse in minutes rather than eons. Elite Dangerous goes for realism, depicting hydrogen filaments as hazardous nebulas that damage unprepared vessels, a nod to the real turbulence found in some dense galactic bridges. These creative liberties aren't just fun, they're thought experiments. By gamifying these structures, developers invite players to ponder, what if we could harness these bridges? What secrets might hide in their depths? Even blockbuster films borrow the aesthetic. The golden threads connecting planets in Doctor Strange mirror the filamentary structure of the cosmic web, while Interstellar's Tesseract scene visualizes higher dimensions as glowing strands, an artistic echo of how gravity might warp these real-life bridges. What's fascinating is how these portrayals circle back to inspire real science. Astronomers studying the Sculptor Wall, a massive galactic filament, jokingly nicknamed it the Laniakea Superhighway after seeing similar terms in sci-fi. The cross-pollination goes both ways when researchers published the first 3D map of the cosmic web. Concept artists for Destiny and Star Citizen immediately incorporated its fractal beauty into their alien skies. This cultural feedback loop reveals a deeper truth. Humanity craves narratives that make the cosmos feel traversable. Ancient cultures linked stars with mythic ropes and silver roads. Today's stories simply swap those for hyperspace conduits and quantum tunnels. The real magic lies in how science feeds these fantasies while gently correcting them. Yes, the bridges exist, but they're subtler, stranger, and more magnificent than any fiction could conjure. Every time a game lets us fly through a nebular bridge or a film dramatizes cosmic filaments, it's not just entertainment, it's rehearsing for a future where understanding these structures might be key to surviving among the stars. Perhaps the most poignant adaptations come from music and abstract art. Composers like Jean Mitchell-Jarre have crafted ambient soundscapes imagining the songs of intergalactic plasma. Low-frequency vibrations no human ear could hear, translated into haunting melodies. Digital artists like Rafik Anadol use telescope data to generate swirling installations where visitors walk through curtains of light modeled on hydrogen filaments. These works don't simplify the science, they elevate it, reminding us that the universe's grandeur isn't just in facts and figures, but in the emotions it stirs. A child seeing a glowing bridge in a planetarium show might not grasp the parsecs or particle physics, but they'll remember the awe. And somewhere in that awe, the next great astronomer or sci-fi visionary might be taking root. The bridge between science and storytelling isn't one way. Just as researchers' discoveries fuel new creative worlds, artists' bold visions push scientists to ask, could we someday detect star-forming knots in filaments as game worlds suggest? Might magnetic fields really braid these structures as paintings imply? The best portrayals, whether in novels, games, or films, aren't those that get every detail right, but those that capture the wonder driving us to study these cosmic threads in the first place. After all, before we can cross a bridge, we must first imagine it's there. These cosmic bridges are more than astronomical wonders. They're the universe's most dynamic classroom, offering masterclasses in physics that no textbook could replicate. Take gravity, for example. In a lecture hall, it's abstract equations and hypothetical scenarios. But out there in the void, these filaments demonstrate gravity's power in action. Delicate hydrogen atoms, spaced meters apart, still managing to coalesce into coherent structures over millions of light years. It's like watching an invisible hand sculpt fog into cables, proving how even the weakest force, given enough time, can build the grandest architectures. Educators at institutions like MIT and Caltech now use bridge simulations to teach orbital mechanics, showing students how galaxies tug on these filaments like children playing tug-of-war with a rope made of smoke. Gas dynamics, a subject that typically lives in dense academic papers, comes alive when you study how hydrogen flows through these bridges. The same principles that govern weather patterns on Earth, like turbulence and pressure gradients, play out across cosmic scales. A fluid dynamics professor at Cambridge famously projected real-time data from the Leo Bridge during lectures, highlighting how gas clumps and eddies mimic ocean currents, just 1 billion times larger and 1 million times slower. These aren't just analogies, they're identical physics operating in extreme environments, helping students grasp universal laws through breathtaking scale comparisons. What makes these bridges unparalleled teaching tools is their visual storytelling. Complex theories like dark matter's role become tangible when students see how filaments bend and warp in ways ordinary matter can't explain. The European Space Agency's educational team created an interactive model where learners adjust dark matter parameters to see how it affects bridge stability, a digital sandbox that's helped demystify one of astronomy's most elusive concepts. Even quantum mechanics gets a cameo. The faint 21-centimeter radiation emitted by bridge hydrogen illustrates electron spin transitions, linking the infinitesimally small to the astronomically vast. The bridges also shatter preconceptions about cosmic isolation. For generations, astronomers depicted galaxies as solitary islands. Now, educators use filament maps to show the intricate web of relationships, like a high school biology teacher revealing the mycelial networks connecting forest trees. This paradigm shift resonates beyond astronomy, influencing how we teach ecology, sociology, and even internet infrastructure. The bridges become metaphors for interconnection, proving that no system, no matter how vast, exists in a vacuum. Perhaps most powerfully, these filaments teach patience. In an era of instant gratification, they demonstrate how the universe works on timescales beyond human intuition. A graduate student might spend their entire career analyzing a single bridges dataset, a humbling reminder that some truths unfold over generations. Yet every discovery, whether it's a star forming in the void or a filament's subtle vibration, adds another piece to the puzzle. And that's the ultimate lesson these cosmic bridges offer, that the universe is always teaching if we're willing to observe, question, and wait for the answers to reveal themselves across the eons. You don't need a PhD or $1 billion telescope to help unravel the mysteries of these cosmic bridges. Some of the most exciting discoveries are happening thanks to amateur astronomers and citizen scientists just like you. Projects like Galaxies Zoo and Zooniverse have turned bridge hunting into a global collaboration, where anyone with an internet connection can sift through telescope data, flagging faint filaments that automated algorithms might miss. It's a modern-day gold rush, except instead of panning for nuggets, volunteers are scanning the cosmic void for wisps of hydrogen that could rewrite our understanding of galactic connections. Take the case of Hanny's Voorwerp, a bizarre green blob of gas discovered by Dutch schoolteacher Hanny van Arkel while she was classifying galaxies as part of Galaxy Zoo. What started as a curious anomaly turned out to be a luminous echo from a quasar, illuminating a previously hidden stream of intergalactic gas. Discoveries like this prove that fresh eyes on old data can spot what professionals overlook. After all, the human brain is still the best pattern recognition machine we've got. Now, specialized projects like Cosmic Web Hunters train volunteers to identify the subtle signatures of bridges in radio telescope data, turning coffee break stargazing into genuine scientific contribution. The tools are more accessible than you might think. Platforms like ISA's Sky or NAS, a worldwide telescope, let you explore high-resolution cosmic surveys from your laptop. No fancy equipment required. Some amateurs have even made breakthroughs using backyard radio telescopes tuned to hydrogen's 21-centimeter wavelength, collecting data that complements professional observations. In Australia, a group of hobbyists collaborating with the Square Kilometre Array team detected unexpected fluctuations in a well-known filament, a finding that later made it into a peer-reviewed paper. It's a reminder that curiosity, not credentials, drives discovery. What's truly revolutionary is how these projects democratize science. A retiree in Tokyo might spot a bridges kink caused by a passing dwarf galaxy. A high school student in Brazil could notice a filament's unusual color gradient, hinting at chemical pollution from ancient supernova. Every observation gets folded into a growing catalog, helping researchers prioritize where to aim their big telescopes next. And the impact goes beyond data. These collaborations are training a new generation of astronomers, proving that the cosmos belongs to everyone willing to look up and wonder. The next great cosmic bridge discovery might not come from a mountaintop observatory, but from your living room. As telescopes like the SKA come online, their flood of data will need more eyes than any professional team could muster. That's where you come in. Whether you're sketching galaxy clusters from a suburban backyard or classifying filaments on a lunch break, you're part of a grand tradition, humans peering into the dark, finding connections where none seem to exist, and reminding us all that the universe still has secrets waiting to be uncovered by anyone brave enough to search. Galaxy clusters are the universe's grand metropolises, crowded, chaotic, and threaded with bridges so dense they make solitary intergalactic filaments look like country backroads. In these dense neighborhoods where hundreds or even thousands of galaxies huddle together, the bridges aren't just connections, they're superhighways of gas, twisted into intricate knots by the gravitational tug of war between massive neighbors. Picture Times Square at rush hour, but instead of people, it's galaxies jostling for space, their bridges crisscrossing like a cosmic subway system, ferrying hydrogen between them at unimaginable scales. These environments are so extreme, they bend the rules of physics as we know them, offering front-row seats to phenomena you'd never spot in quieter corners of the cosmos. One of the most startling discoveries in clusters like Coma or Perseus is how bridges behave under pressure. In isolation, a filament might stretch peacefully for millions of years. But in a cluster, it's like sending a silk ribbon into a hurricane. The gas gets whipped into turbulent whirlpools, shocked by supersonic winds from galaxy collisions, and even lit up by the intense radiation of quasars. Astronomers call this RAM pressure stripping. where the sheer force of a galaxy's motion through the cluster yanks gas from its bridges, leaving behind glowing trails like cosmic breadcrumbs. These violent interactions aren't just destructive, they're creative. The same turbulence that shreds filaments can also compress hydrogen into dense pockets, sparking bursts of star formation right there in the void. It's a paradox. The places where bridges are most battered often become the most fertile ground for new stars. The complexity doesn't stop there. In clusters, bridges rarely connect just two galaxies. They branch, merge, and tangle into sprawling networks. The Phoenix cluster, for instance, hosts a filamentary web so vast it resembles a spider's silk draped across the entire region. Some strands funnel gas toward a central supermassive black hole, feeding it like arteries nourishing a heart. Others loop around galaxies in bizarre rings, their curvature tracing the aftermath of ancient collisions. These structures are more than just pretty patterns. They're fossil records of the cluster's violent history. By mapping them, scientists can reconstruct events from billions of years ago, like detectives piecing together a crime scene from scattered clues. What makes cluster bridges truly unique, though, is their role as cosmic thermometers. The gas here isn't just hot, it's scorching, reaching temperatures of tens of millions of degrees, so intense it emits X-rays detectable across the universe. By studying how these bridges glow in different wavelengths, astronomers can measure the cluster's energy budget, tracking how heat ripples through the filaments like sound waves in a pipe. Some bridges even reveal cold fronts, sharp boundaries where hot and cool gas collide, creating shock waves that ripple through the cluster for eons. These features aren't just curiosities, they're clues to how clusters grow, how they recycle their gas, and why some galaxies within them thrive while others starve. Yet for all their ferocity, these bridges also hint at an underlying order. Despite the chaos, filaments in clusters often align with the invisible scaffolding of dark matter, their paths tracing the hidden architecture of the cosmos. It's as if the universe, even in its most riotous neighborhoods, still follows a blueprint, one where dark matter's ghostly fingers guide the flow of gas, and where bridges, no matter how battered, endure as the ultimate connectors. For astronomers, that's the real gift of galaxy clusters, a chance to see the cosmic web not just as a theory, but in action, its filaments stretched, twisted, and tested to the limit, and still holding the universe together. Among the countless cosmic bridges threading the universe, a few defy all expectations, behaving in ways that leave even seasoned astronomers scratching their heads. Take the mysterious filament linking galaxy clusters Able 399 and Able 401, for instance. Observations revealed gas within this bridge reaching temperatures over 80 million degrees hotter than the cores of some stars, with no obvious heat source nearby. It's like stumbling upon a frozen river where sections are inexplicably boiling, challenging everything we know about how intergalactic gas should behave. Even more perplexing are the bridges exhibiting forbidden motions, where hydrogen flows against the gravitational tide, as if some unseen hand were stirring the cosmic pot. One leading theory points to dark matter's hidden machinations. Could certain types of dark particles interact with hydrogen in ways we haven't yet detected, transferring energy like invisible conductors? Alternatively, these anomalies might trace back to primordial magnetic fields, relics from the universe's infancy, woven through the filaments like invisible wires, channeling and heating the gas. Then there's the enigma of ghost flows, bridges where gas moves in synchronized waves across millions of light years, as if responding to a cosmic drumbeat no instrument can hear. Some researchers speculate these could be echoes of ancient collisions, vibrations from long ago galactic encounters still rippling through the filaments like notes from a struck gong. The most tantalizing puzzles come from bridges that flicker unpredictably. In the Lynx Cancer void, a filament's hydrogen emission dims and brightens over decades far too quickly for traditional models to explain. It's as if someone were switching a cosmic lamp on and off, suggesting processes we've yet to imagine. Others show bizarre chemistry, with trace elements like neon or nitrogen appearing in concentrations that shouldn't exist so far from galaxies. Could these be the smudged fingerprints of exotic stellar explosions, or even signs of previously unknown particle interactions? What makes these mysteries so thrilling isn't just their strangeness, it's their potential to rewrite physics. Every anomalous bridge is a natural laboratory, testing our theories under conditions no earthbound experiment could replicate. They hint at forces beyond gravity and electromagnetism, at energy transfers that defy conventional thermodynamics, and perhaps even at dark matter's true nature. For scientists, these aren't just cosmic oddities. They're breadcrumbs leading toward the next great breakthrough, scattered across the darkness between galaxies. And with each new telescope that comes online, we edge closer to deciphering their secrets or uncovering even deeper questions we haven't yet learned to ask. These cosmic bridges aren't just fascinating structures, they're shaking the foundations of astrophysics, forcing scientists to rewrite the rulebook on how galaxies form and evolve. For decades, the prevailing theory suggested galaxies grew primarily by gobbling up nearby gas or merging with smaller neighbors in their immediate vicinity. But these vast hydrogen filaments tell a different story, one where galaxies are nurtured by rivers of gas flowing in from intergalactic space, sometimes from millions of light years away. It's as if we've discovered that trees in a forest aren't just growing from local soil, but are secretly being fed by underground aquifers spanning entire continents. One of the most startling revelations is how these bridges challenge our understanding of the missing baryon problem. Scientists have long known that about half the ordinary matter predicted by cosmological models was unaccounted for, not hiding in stars or galaxies, but seemingly vanished. These filaments now appear to be the universe's secret storage units, locking away that missing matter in their diffuse strands. The gas is so spread out, it escaped detection for years, like trying to spot individual water molecules in a fog bank. This discovery doesn't just solve a mystery, it completely changes how we calculate the universe's mass budget, proving that what we once thought was empty space is actually brimming with hidden structure. The bridges also append assumptions about galactic life cycles. Traditional models assumed galaxies had finite fuel supplies, destined to fade as they exhausted their gas reserves. But these filaments act like cosmic intravenous drips, continuously supplying fresh hydrogen to star-forming regions. Take the case of the Spiderweb galaxy, a massive system connected to multiple filaments. Observations show it's forming stars at an astonishing rate, not from internal gas, but from this external supply, like a car running not on its tank, but on fuel piped in from distant reservoirs. This forces astronomers to reconsider what triggers and sustains star formation, adding intergalactic gas flows as a critical variable in their equations. Perhaps the most profound implication lies in dark matter's role. Simulations show these filaments align perfectly with dark matter's gravitational scaffolding, but with puzzling discrepancies. Some bridges are thicker than dark matter alone should allow, hinting at unknown forces at play. Others show gas moving in ways that defy gravitational predictions, as if invisible magnetic fields or quantum effects are influencing the flow. These anomalies suggest our models of dark matter might be incomplete, missing some subtle property that only reveals itself in these extreme, low-density environments. Every new bridge mapped is another data point in this cosmic detective story, each strand of hydrogen potentially holding clues to the universe's most elusive substance. What's emerging is a radical shift in perspective. Galaxies aren't isolated ecosystems, but interconnected nodes in a vast cosmic network. Their evolution isn't determined solely by local conditions, but by their position in this web and the bridges that tie them to it. This realization is transforming astrophysics from a science of individual objects to a study of relationships, a celestial sociology where connections matter as much as the galaxies themselves. And as telescopes grow more powerful, each new filament discovered promises to refine, or perhaps revolutionize, our understanding of the universe's grand design. The hydrogen threading these cosmic bridges is anything but comet churns with storms and currents, a sprawling weather system operating on scales so vast, our entire solar system would be a speck in its atmosphere. Imagine the jet streams on Earth, but instead of guiding airliners, these intergalactic winds shape the destiny of galaxies, carrying heat, energy, and raw star fuel across millions of light years. The gas doesn't just flow smoothly, it ripples with turbulence, forming pockets of high pressure that glow fiercely in X-rays, while cooler regions condense into dense knots where new stars flicker to life. This isn't just weather, it's a celestial climate system, one that dictates whether galaxies thrive or stagnate over billions of years. Take the famous Sculptor Wall, a filament where astronomers have spotted hurricane-like vortices swirling through the gas. These aren't driven by temperature differences like earthly storms, but by the gravitational tug of war between galaxies. As neighboring clusters pull on the filament, they send shockwaves rippling through the hydrogen, creating whirlpools that can persist for epochs. Some of these turbulent zones heat the gas to millions of degrees, causing it to emit X-rays visible to space telescopes like Chandra. Other stretches remain eerily cold, their hydrogen so chilled it barely registers above the cosmic microwave background. The contrast is staggering, like finding Arctic blizzards and desert heatwaves coexisting in the same vast river. This intergalactic weather doesn't just happen, it leaves fingerprints. When galaxies siphon gas from these filaments, they're not drawing from a uniform reservoir. Cool, dense clumps funnel into star-forming regions like monsoons feeding a desert oasis. While hot, turbulent streams might suppress star birth entirely, their violent motion preventing gas from settling into stable clouds. The Andromeda Galaxy's southern rim bears the scars of this cosmic meteorology, a frothy, superheated zone where a high-pressure filament collides with its outer disk, creating a shock front that glows brighter than 1,000 supernovae. Meanwhile, in quieter filaments like those threading the Lynx Cancer void, the gas is so placid it barely stirs, allowing galaxies to sip slowly, like dew gathering on a spider's web. The most dramatic weather events occur when filaments collide. In the crowded core of the Coma cluster, astronomers have spotted a cosmic cold front, stretching over 500,000 light-years, a wall of cooler gas plowing through a sea of hot plasma like a glacier grinding through the ocean. The boundary between them crackles with magnetic fields, generating auroras that would dwarf entire galaxies if human eyes could see them. These collisions aren't rare, they're part of the filament life cycle, shaping how gas is distributed across the cosmic web. A single merger can compress a bridge into a star-forming frenzy or tear it apart entirely, scattering hydrogen into the void like mist in a gale. What makes this weather so pivotal is its long-term impact. Just as Earth's climate shapes ecosystems, these intergalactic patterns dictate galactic evolution. A galaxy tethered to a turbulent filament might see its star formation flicker like a candle in the wind, while one connected to a calm, steady flow could flourish for eons. Some researchers now suspect that our own Milky Way's quiet middle age, its star formation neither too frantic nor fully dormant, might trace back to the temperament of the filaments it's entwined with. After all, galaxies aren't just products of their environment. They are passengers on these atmospheric rivers, riding currents older than time itself. The study of this cosmic meteorology is still in its infancy, but already it's rewriting our understanding of galactic ecology. By mapping temperature gradients, tracing shock fronts, and modeling gas flows, astronomers are piecing together a grand unified theory of how the universe's largest structures breathe, churn, and change. Every new observation adds another layer to the forecast, revealing a universe more dynamic and interconnected than we ever dreamed, where the weather isn't just overhead, but woven through the fabric of space itself. To truly grasp the uniqueness of these cosmic bridges, we need to see how they fit into the universe's broader scaffolding, like understanding how a single strand of silk compares to the entire spider's web. Superclusters, those sprawling metropolises of galaxies, might seem similar at first glance, but there's a key difference: scale and purpose. Where superclusters are the neighborhoods, bridges are the roads connecting them. Take the Laniakea supercluster, home to our Milky Way, a vast collection of galaxy clusters bound by gravity. While superclusters are destinations, bridges are the highways that feed them, channeling raw hydrogen into these cosmic cities to fuel their growth. Superclusters are where galaxies congregate. Bridges are how they stay supplied. Then there are voids, the universe's empty deserts, regions so devoid of matter that some stretch hundreds of millions of light years across. At first glance, voids seem like the opposite of bridges, but they're deeply connected. Bridges often outline voids, tracing their edges like ivy clinging to the walls of a canyon. The Boötes void, for instance, isn't just a blank spot. It's encircled by filaments that act like cosmic retaining walls, funneling gas and galaxies away from the emptiness. Voids are the negative space that gives bridges their shape, the silence between the notes in the cosmic symphony. Dark matter halos present another fascinating contrast. These invisible cocoons surround galaxies, their gravity holding stars and gas in place. But while halos are localized, each galaxy wrapped in its own shroud, bridges are the threads stitching halos together. Think of halos as personal atmospheres and bridges as shared trade routes. The real magic happens where they intersect. Bridges pierce through halos, delivering fresh hydrogen that galaxies then capture and mold into stars. Without halos, galaxies would lose their gas. Without bridges, they'd run out of fuel entirely. The most striking distinction lies in visibility. Superclusters and voids reveal themselves through the galaxies they contain or lack. Dark matter halos betray their presence by bending light, but bridges, they're ghosts, detectable only through their faint radio whispers or when backlit by distant quasars. This elusiveness makes them the universe's hidden infrastructure, the framework that shapes everything else, yet remains the hardest to see. What ties all these structures together is their interplay. Superclusters grow where multiple bridges converge, like cities at river junctions. Voids expand as bridges drain matter from their interiors. Halos evolve by siphoning gas from the filaments that thread through them. It's a dynamic, interconnected system where no structure exists in isolation. The bridges aren't just another feature of the cosmos, they're the glue that binds all the others into a coherent whole, the delicate threads weaving the universe's grand tapestry. The ingredients for life might be hitching rides across the universe on these cosmic bridges, turning what we once saw as empty voids into interstellar superhighways for biological building blocks. Picture this: complex organic molecules, forged in the fiery hearts of distant galaxies, getting swept up in stellar winds and ejected into these filaments, only to be delivered millions of years later to entirely new galactic neighborhoods. Astronomers have already spotted telltale signs in the gas, including traces of formaldehyde, methanol, and even simple amino acids clinging to hydrogen like dust on a spider's web. These discoveries shatter old assumptions that life's precursors are confined to planetary systems, suggesting instead that the raw materials for biology could be as widespread as the cosmic web itself. What makes this idea revolutionary isn't just the presence of these molecules, it's how bridges might protect them during their epic journeys. In open space, harsh radiation would tear complex compounds apart. But inside a filament's denser knots, hydrogen acts like a cosmic Faraday cage, shielding delicate chemistry from destructive forces. Simulations show certain regions of these bridges could maintain temperatures and pressures strikingly similar to those in molecular clouds where stars form, essentially providing interstellar incubation chambers where prebiotic chemistry can persist for eons. The implications are staggering. Instead of life's ingredients arising independently in isolated pockets, they might be shared resources, dispersed across galaxies like seeds carried by a celestial river. Consider the evidence mounting from unexpected places. When the ALMA telescope analyzed light passing through a filament near the Milky Way, it detected the spectral fingerprints of cyanide compounds toxic to humans, but crucial for forming nucleobases, the backbone of DNA. Another study found glycolaldehyde, a simple sugar, in a bridge stretching toward the Whirlpool Galaxy. These aren't random contaminants. They're the exact molecules that, under the right conditions, can assemble into ribose, amino acids, and other life-critical compounds. The bridges aren't just passive conduits, they're cosmic assembly lines where radiation and turbulence might actually encourage molecules to link into ever more complex structures as they travel. This reshapes our understanding of life's potential distribution. If bridges can ferry organic material between galaxies, then life, or at least its chemical precursors, might be far more universal than we imagined. A planet forming in one galaxy could inherit ingredients synthesized in another, its chemistry pre-seasoned by interstellar travel. Some astrobiologists even speculate that extremophile microbes, frozen in dormant states within cometary ice, might survive these crossings, turning bridges into vectors not just for chemistry, but for biology itself. It's a controversial idea, but not implausible. Tardigrades, Earth's toughest microorganisms, can survive the vacuum of space. Why not a similar organism, encased in a protective hydrogen cocoon, riding a filament for millennia? The ultimate test may come when we analyze bridges near young planetary systems. If telescopes find prebiotic molecules concentrated where filaments intersect with protoplanetary disks, it would strongly suggest these structures aren't just bystanders in life's story, they're active participants, delivering the universe's recipe book to any world with the right conditions to read it. Until then, every newly discovered organic compound in these filaments adds another piece to the puzzle, hinting that the difference between a sterile cosmos and one teeming with life might come down to the silent, invisible highways stitching it all together. The pursuit of knowledge about these cosmic bridges comes with profound responsibility, not just to science, but to the shared heritage of our night skies. Modern astronomy walks a delicate tightrope. Every new telescope array or radio dish built to study these filaments risks adding to the growing light and radio pollution that increasingly obscures our view of the universe. Consider Chile's Atacama Desert, home to some of the world's most advanced observatories. While its telescopes peer deeper into hydrogen bridges than ever before, the region's once pristine darkness now glows faintly from facility lighting and nearby infrastructure. This isn't just an aesthetic loss, it's a scientific one. The same artificial skyglow that drowns out the Milky Way also interferes with sensitive observations of intergalactic gas, like trying to study a candle's flame while someone shines a flashlight in your eyes. The challenge extends beyond visible light. Radio telescopes hunting for hydrogen's faint 21-centimeter signal must now compete with humanity's electronic chatter, from satellite constellations to 5G networks. A single cell tower's stray emissions can corrupt months of filament data, like static obscuring a whispered secret. The square-kilometer array, poised to revolutionize bridge research, was deliberately placed in remote South African and Australian outbacks, shielded by radio-quiet zones larger than entire countries. Yet even these safeguards face pressure as wireless technology expands, prompting astronomers to lobby for international protections akin to UNESCO World Heritage Sites, but for the electromagnetic spectrum. What's at stake isn't just professional research. For millennia, humans have looked up and seen not just stars, but stories, constellations woven into cultures, from Navajo star maps to Aboriginal Dreamtime traditions. These bridges between galaxies mirror the bonds these celestial narratives created between generations. When light pollution erases the stars, it doesn't just hinder science, it severs a connection to our collective past. Indigenous astronomers voice particular concern, noting how disappearing stars threaten living knowledge systems that have tracked celestial patterns for centuries. Their perspective reminds us that the night sky isn't a laboratory, it's a library, a cathedral, and a birthright. Emerging technologies offer hope. Adaptive lighting systems that dim or shield emissions when telescopes are active already protects major observatories. Laser satellites could one day replace radio transmissions for some communications, reducing interference. Citizen science initiatives like Globe at Night engage millions in monitoring sky brightness, creating grassroots pressure for darker skies. Perhaps most promising are advances in data processing, where AI filters out human-made noise, salvaging observations that would have been lost a decade ago. The ethical path forward requires reimagining progress not as conquering frontiers, but as careful stewardship. Just as we protect ancient forests for their ecological and cultural value, we must safeguard our view of the cosmos, not only for the secrets these bridges might reveal about dark matter or galactic evolution, but for the humility they inspire. There's profound wisdom in balancing discovery with preservation, ensuring that while we reach for the stars, we never lose sight of them. After all, the same delicate filaments connecting galaxies also connect us, to each other, to our ancestors, and to future generations who deserve their own chance to gaze upward and wonder. These cosmic bridges do more than connect galaxies. They collapse the illusion of separation that has defined humanity's cosmic perspective for centuries. We've long imagined galaxies as isolated islands, adrift in an indifferent void, but these filaments reveal a universe stitched together by invisible threads, where every major structure is part of an intricate embrace. It's a humbling shift. The same forces that bind stars into galaxies also weave galaxies into something grander, suggesting that connection isn't the exception in the cosmos, it's the rule. Consider what this means for our search for meaning. For millennia, humans have grappled with feelings of cosmic loneliness, gazing at the stars and wondering if we're the only witnesses to this vastness. Yet these bridges whisper a different story, one where even the mightiest galaxies are interdependent, drawing life from shared rivers of gas. If the universe's largest structures rely on connection to thrive, might there be a lesson in that for us? Indigenous cosmologies have long spoken of celestial pathways, the Aboriginal songlines, Norse Bifrost, or Maya world trees, not as myth, but as intuitive recognitions of a truth science is now uncovering, that existence at every scale is relational. The bridges also challenge our notions of time. A single filament may persist for billions of years, outlasting civilizations, species, even planets. Yet within that span, it's never static. It breathes, flows, and adapts, a celestial embodiment of the Buddhist concept of impermanence within continuity. To study these structures is to confront time not as a line, but as a tapestry where the hydrogen atoms passing through a bridge today might one day ignite as stars in a galaxy yet to form. We're not just observers of this process, we're made from it. Every element in our bodies, the oxygen in our lungs, the iron in our blood, was forged in stellar furnaces and likely transported across similar bridges before finding its way into Earth's primordial soup. Perhaps most profoundly, these filaments blur the boundary between the mundane and the cosmic. The same physics governing a raindrop's fall or a river's meander shapes these galactic connections: gravity, motion, turbulence playing out across scales so vast they defy intuition. It's a reminder that the universe isn't just out there. Its patterns echo everywhere, from the branching of neurons in our brains to the structure of mycelial networks underfoot. The bridges become metaphors, inviting us to see our own lives as part of a larger web, not insignificant because we're small, but integral because we're connected. In the end, these threads of hydrogen do more than fuel galaxies. They reframe our place in the cosmos, not as accidental specks, nor as the universe's sole purpose, but as conscious participants in an ancient, evolving dance of matter and energy. To look up and know that the void isn't empty but threaded with invisible bonds changes everything. It suggests that even in the grandest scales, the universe thrives on relationship, and in that, we might find both humility and belonging. Imagine holding the universe in your hands, pinching to zoom through a shimmering filament of hydrogen gas, rotating it to see how it connects two distant galaxies, then diving straight through its core like a cosmic submarine. This isn't science fiction. It's the cutting edge of astronomy education, where websites and apps transform terabytes of telescope data into interactive journeys anyone can take from their phone or laptop. Platforms like NASA Eyes on the Universe or the European Space Agency's Gaia Sky don't just show these bridges, they let you feel their scale, their texture, their place in the cosmic web. With a swipe, you can toggle between the cold blue glow of hydrogen emissions and the fiery gold of dark matter simulations, revealing how invisible forces sculpt these structures. It's a quantum leap from static textbook images to dynamic exploration, where curiosity becomes your compass and every click unveils another layer of the universe's hidden architecture. The magic lies in how these tools democratize discovery, where once only researchers with access to supercomputers could analyze bridge structures. Now a high school student in Jakarta or a retiree in Lisbon can trace filaments across billions of light years using tools like the Sloan Digital Sky Survey's Voyager app. Want to compare the turbulent Leo bridge with the serene filament threading the Boots void? A few taps overlay them side by side, complete with velocity graphs showing how gas streams differ. These platforms often include citizen science features. Two flagging oddities in the data might lead to a real discovery, like the amateur who spotted a kinked filament in the Cosmic Web Explorer app that later proved to be evidence of a rare dark matter interaction. What makes these experiences transformative isn't just the visuals, it's the context they provide. Hover over a bridge in the space engine software, and pop-ups explain how its hydrogen density compares to Earth's atmosphere a trillion times thinner, or how long it would take a spacecraft to traverse it at light speed millions of years. Some apps like Universe Sandbox go further, letting users tweak gravity's strength or dark energy's influence to see how filaments stretch or snap under different cosmic rules. It's astrophysics as a choose-your-own adventure, where trial and error reveal why our universe's particular constants allow these delicate structures to exist. The most profound impact might be emotional. There's an awe that clicks when you manipulate a 3D model of the Pisces Cetus filament, realizing those pixels represent real gas, actual atoms older than Earth binding galaxies in an unfathomably slow dance. Apps like Nightshade even integrate VR, allowing users to stand inside a bridge's cross-section, watching data particles swirl like fireflies as a narrator explains how gravity and dark matter orchestrate the flow. For educators, this is gold. Students who glaze over at equations light up when they fly through the same structures they're learning to calculate. Yet these tools aren't just fancy toys, they're reshaping research itself. The Aladdin Sky Atlas lets astronomers annotate bridges collaboratively, tagging shock fronts or star-forming knots like cosmic road signs. Meanwhile, the Cosmostat platform uses machine learning to predict filament connections in unexplored regions, turning exploration into a treasure hunt where X might literally mark a previously unknown hydrogen highway. As these tools evolve, incorporating real-time data from telescopes like JWST, they're blurring the line between professional and public engagement, creating a world where mapping the cosmic web could become as crowd-sourced as bird-watching. The message is clear: understanding the universe no longer requires a PhD, just curiosity and a device. These interfaces are more than software. They're portals, turning abstract science into something tactile, immediate, and deeply human. Every zoom, rotation, and simulation whispers the same revelation, that the grandest structures in existence aren't beyond our grasp. They're just a click away, waiting to remind us how wonderfully, humblingly connected everything truly is. Unlocking the secrets of cosmic bridges has become one of astronomy's great collaborative achievements, a planetary effort where researchers from Tokyo to Cape Town share data, tools, and sleepless nights chasing whispers of hydrogen across the void. Consider the landmark study of the Able 3391-95 filament. Japanese radio telescopes first mapped its structure. Chilean instruments measured its chemical makeup, Australian supercomputers simulated its dynamics, and American satellites pinpointed its X-ray emissions. No single nation or even continent could have pieced together this puzzle alone. It's science without borders, where PhDs and citizen scientists alike contribute to something larger than any individual could achieve, proving that the universe's grandest structures demand equally grand alliances to understand them. The coordination happens in ways both high-tech and surprisingly personal. Every morning, astronomers at the Mir Kayati Array in South Africa wake up to emails from colleagues in India who observed their shared filament during nighttime hours, creating an unbroken chain of observation. Data from Mexico's Large Millimeter Telescope flows into shared servers where French theoreticians compare it against dark matter models, while Brazilian grad students annotate unexpected gas clumps using open-source tools developed in Germany. This isn't just parallel work, it's deeply interdependent, like a global relay race where the baton is a stream of photons collected from across the electromagnetic spectrum. Even language barriers dissolve under standardized data formats and the universal lexicon of mathematics, with papers on filament turbulence routinely listing co-authors from a dozen countries. What's beautiful is how these collaborations transcend academia. When the ALMA telescope needed help classifying filament structures, they launched a citizen science project that enlisted gamers, artists, and retirees, people whose pattern recognition skills spotted anomalies algorithms missed. One retired engineer in Norway identified a peculiar kink in the Perseus-Pisces filament that turned out to be evidence of an ancient galactic collision. Meanwhile, indigenous astronomers in Australia and Hawaii contribute traditional knowledge about celestial navigation, offering perspectives on cosmic connectivity that predate telescopes by millennia. These bridges between galaxies, it turns out, are also building bridges between cultures, disciplines, and ways of knowing. The challenges are as illuminating as the successes. Time zone differences mean crucial video calls happen at 3 a.m. for someone. Political tensions occasionally delay equipment shipments. Some teams work with budgets a fraction of others, relying on ingenuity to fill gaps, like the Kenyan engineers who modified radio receivers from old cell towers to help monitor a filament's radio emissions. Yet these hurdles only highlight science's unique power to foster cooperation where other endeavors fail. Sharing a eureka, a moment like when teams on 3 continents simultaneously confirmed gas flowing at supersonic speeds through a filament, creates bonds no border can sever. At its heart, this global effort mirrors the very structures it studies. Just as hydrogen filaments link galaxies into a vast, living network, these collaborations weave human curiosity into a tapestry of collective discovery. Each observation, simulation, and insight is a node in an ever-growing web of knowledge, one that proves how much more we can achieve when we recognize that in the face of the cosmos, we're all on the same team. The bridges out there remind us of the bridges we're building here, light years closer to home. The Intergalactic Hydrogen Bridge isn't just an astronomical phenomenon, it's a cosmic revelation, rewriting how we understand our place in the universe. These delicate threads of gas, suspended between galaxies like celestial tightropes, represent something far grander than their wispy appearance suggests. They're the universe's hidden architects, quietly shaping galactic destinies over eons while preserving chemical secrets from the dawn of time. Every new discovery peels back another layer, showing us that what we once perceived as empty voids are actually vibrant highways humming with activity, where hydrogen atoms older than our solar system journey between galaxies, carrying the raw materials for new stars, planets, and possibly even the building blocks of life. What makes these bridges truly extraordinary is their duality. They're both ancient and ever-changing. The hydrogen within them dates back nearly 14 billion years, pristine remnants of the universe's fiery birth. Yet these filaments are constantly evolving, responding to galactic collisions, dark matter's invisible pull, and the relentless expansion of space itself. They're cosmic time capsules and living ecosystems in one, offering snapshots of the past while actively participating in the present. The bridge connecting the Andromeda and Triangulum galaxies, for instance, shows chemical traces from generations of supernova stellar explosions that occurred before Earth formed, mixed with fresh gas currently streaming toward new star-forming regions. It's a reminder that the universe doesn't just have a history, it's actively writing its next chapter through structures like these. This exploration has only just begun. With next-generation telescopes like the Square Kilometre Array coming online, we're on the verge of mapping thousands more filaments in unprecedented detail. Each one could hold surprises, perhaps bridges that defy our models of dark matter, or filaments so packed with organic molecules they resemble interstellar chemical factories. Some theorists even speculate we might discover dark bridges, filaments dominated by invisible matter that could finally reveal dark matter's true nature. The possibilities stretch as far as the bridges themselves, limited only by our imagination and technology's steady advance. Yet beyond the science lies a deeper resonance. These bridges symbolize connection in a universe that often feels incomprehensibly vast. They remind us that nothing, not galaxies, not stars, not even the atoms in our bodies, exists in isolation. We're all part of an intricate web spanning space and time, linked by forces both seen and unseen. So when you next gaze at the night sky, let your imagination travel those invisible threads. Trace them from star to star, galaxy to galaxy, until the distance between out there and here doesn't feel so immense, because in learning how the universe connects itself, we might just rediscover how connected we are to it and to each other.